All right, guys. So obviously in 6.5 part 1, we got introduced to the basic idea of what a rational functions graph looked like, as well as how we could identify transformations in a rational function. In part 2, what we're going to focus on is how the equation more closely correlates to the graph. In other words, how can we use the equation to create a graph, talking about some of the key features and so on. To get started, we're just going to talk about what the domain of a rational function is. So, when we talk about the domain of a rational function, we typically say that it is all real numbers except for our domain restrictions. Which should kind of make sense. If our domain restrictions are what x cannot equal, then obviously those cannot be part of our domain. But besides those numbers, everything else works. So let's go ahead and do some examples of this. And it asks for interval notation. We're not going to do interval notation, although you can if you'd like to. So number 1, we've got f of x equals 1 over x minus 4. Our only restriction here is that x cannot equal 4. So what we're going to say is that our domain is all real numbers with x not being equal to 4. In other words, every number except 4 is going to work for us. So let's do the same thing on number 2. Here we've got two domain restrictions, which is that x cannot equal -3 and that x cannot equal 7. So again, we're going to say that our domain is all real numbers with the two exceptions that x cannot equal those two values. And finally, for the third function, we've got x squared minus 7x plus 12 over x squared plus 9x plus 20. Notice that it is not factored, so let's go ahead and factor it real quick. For our numerator, it would factor to be x minus 3 and x minus 4. For denominator, x plus 4 and x plus 5. So our two restrictions are going to be that x cannot equal -4 and that x cannot equal -5. And so our domain then is going to be all real numbers with those two exceptions. Now, what we're going to see is that those exceptions where x cannot equal a value is really going to actually become one of two things. It's either going to be a whole or it's going to be a vertical asymptote. So let's go ahead and define what exactly is an asymptote. Well, an asymptote is an imaginary line. It's not actually a part of our function that a function approaches but never reaches. In other words, you get really, really, really close to the value, but you never actually get to it. Okay, so let's talk about some of those key features that I was mentioning before. We're going to talk about wholes as well as vertical asymptotes and roots. So let's take a look at it in the context of this equation that I've got for us right here, which is that f of x is equal to x squared plus 2x minus 3 over x squared plus 7x plus 12. And it tells us even right here that our first thing that we need to always do is make sure that we factor it completely. So we've got x plus 3 and x minus 1 as our factors for our numerator. And then for denominator, we're going to have x plus 3 and x plus 4. All right. So let's go ahead and use that to answer or to talk about each of these different key features. The first thing we're going to talk about is a whole. A whole is also sometimes referred to as a removable discontinuity. And the reason it's referred to that is that it's a factor which cancels out from both numerator and denominator. In other words, in this case, our x plus 3, that factor of x plus 3 is going to cancel out. that leaves us with a whole at an x value of -3. So in other words, our domain restriction would have been that x cannot equal -3, which should make sense because that means that there's a hole there. That's why x cannot equal -3. Now, we also like to find the y value for holes. And in order to find the y value for your hole, we're going to take -3 and put it in for x in the remaining rational function. In other words, we're going to take -3 minus 1 over -3 plus 4. And that's going to become -4 over 1, which is just -4. In other words, this function that we had is going to have a hole at the point -3, -4. Now, you can see on this graph the way that we will indicate a hole. Obviously, this one is at a different point, but notice that we use an open circle, and then we simply connect our function on either side of it. What that means is that our function gets really, really close to whatever that point is, but it never actually has a point there. It has a point everywhere to the left, everywhere to the right. I mean, right up until that point, but not actually at it. Okay, so now let's go ahead and use our function that we have left. So x minus 1 over x plus 4 is what we are left with once we cancel out that factor. So if a factor does not cancel and is left in our denominator, then it's going to create a vertical asymptote. In other words, our other domain restriction was that x cannot equal -4. So we're going to have a vertical asymptote at x equals -4. So a vertical asymptote, if you remember from the previous section, where those imaginary lines that are going up and down are a vertical line. And so we'd have a vertical asymptote at that value. Okay. And for this last part for roots, that's going to be anything left in our numerator. So if a factor does not cancel and is left in the numerator, then it becomes a root. In other words, if x minus 1 is still left in our numerator, then x equals 1 is a root. In other words, we have a root at 1, 0. All right, so as a reminder, roots are just x-intercepts, so if you needed that refresher, there you go. So to summarize, when we talk about the domain of a rational function, it's going to become one of two things. When we say x cannot equal -3 and x cannot equal -4 for our domain of our rational function. So again, all real numbers except or with these exceptions. They're going to become one of two things. Either they're going to become a hole if it cancels, or you're going to get a vertical asymptote, which as an abbreviation for that, we will often write VA for a vertical asymptote. All right. Now, in addition to our vertical asymptotes, if you remember, we also had those horizontal asymptotes. And in fact, we also have slant asymptotes. If you're wondering what a slant asymptote looks like, the only place we really would have seen that would have been on number 5 when we were talking about in behavior, where when we were looking at this graph, we noticed that the graph does tend towards positive and negative infinity as it reaches the ends of the graph. But instead of having a vertical asymptote, this graph actually has a slant asymptote. In other words, it has a line with a slope as the asymptote rather than just having a horizontal line like we would have on number 4. So if we want to find the horizontal or slant asymptotes for a function, we're going to have to do either synthetic or more commonly long division. In fact, long division is probably going to be the one that we're going to have to use. Once we're done dividing, whatever is not part of the remainder is going to be the asymptote for that particular function. So let's go ahead and work through some examples finding our asymptotes being either slant or horizontal for a few different functions. Starting with number 4, we've got f of x equals x squared minus 5x plus 6. So as a reminder, when you do long division, we'll take our numerator and put it underneath the division bar. So x squared minus 5x plus 6. And then we're dividing by x minus 4, which we'll put to the left. Remember, your goal is to get x to match up with x squared, so that would be to multiply by x. And then make sure you distribute that all the way through, so that would be x squared minus 4x. Now remember that you are subtracting then underneath, so we'll change both of our signs to be opposites. And that's going to give us negative x plus 6 to still work with. Now once again, our goal is to get x to match up with our negative x. We'll do that by multiplying by negative 1. When we distribute that through, we're going to get negative x plus 4. But then remember, you are subtracting, so change both of your signs to be opposites. So that's going to be a positive x and a negative 4. And then when we subtract there, we're going to end up with positive 2 as our remainder. Remember, your remainder goes over your divisor, so that would be 2 over x minus 4. So our slant asymptote is going to actually be through this non-remainder portion. In other words, y equals x minus 1 is going to be our asymptote. Now, if you think about what y equals x minus 1 would look like on a graph, it would actually just be a line with a slope of 1. In other words, it's not a horizontal line, it's not a vertical line, it's actually a line that's got a slant to it. We also sometimes call slant asymptotes oblique asymptotes. I will usually refer to them as slant, but if you see the word oblique anywhere, that's the other way that they can be described. Now, the remaining rational function is that now, if we would like to, we can now use that function that we just got by dividing. So x minus 1 plus 2 over x minus 4 in order to find all of the other key features of our graph, including the vertical asymptotes and x-intercepts. All right, let's do another example. Let's take a look at number 5 here. So number 5, we've got f of x equals 2x squared minus 7x plus 6 divided by 2x squared minus 3. So again, we'll go ahead and put the numerator underneath of our division bar, and the 2x squared plus 0x minus 3 to the right, or to the left of it, rather. Now notice that I put 0x in there. You really don't need to do that, but it does make it a little bit easier to remember your placeholders. And our goal is to get 2x squared to match up with 2x squared. They already do match each other, so really we just need to multiply by 1. And when we distribute the 1 through, obviously we're just going to get what our expression was. So 2x squared, a 0x, and a negative 3. And then remember that you are subtracting, so change all of your signs. So that's going to leave you with negative 7x plus 9. Which at this point, our remainder has a lesser degree than our divisor, which means that we are actually done. There is our remainder, so a negative 7x plus 9 over that 2x squared minus 3. So this time, if you look at our asymptote being that portion of the function which is in front of the remainder, we're going to say that our asymptote is through y equals 1. This time, if you think about what type of line that would be, y equals 1 would be a horizontal line. And if you're not sure, just go ahead and graph it. Now, the remaining rational function then that we could use to help us with the other key features of our graph is going to be that f of x is equal to 1 plus negative 7x plus 9 over 2x squared minus 3. All right, one last example to take a look at here. We've got f of x is equal to 5x plus 6 divided by x squared minus 3x minus 4. So again, same setup. We'll take our numerator, put it underneath our division bar, and then the x squared minus 3x minus 4 is going to go outside to the left. So now our goal is to now try to get x squared to match up with 5x, which actually isn't going to happen. In fact, at this point, there isn't anything more we can do. What we're dividing is already a lesser degree than our divisor, which means that actually this entire expression is just going to be a remainder. So it's actually not going to change at all. It's still going to be 5x plus 6 over x squared minus 3x minus 4. However, we still do need something in front of this in order to see what our asymptote is going to be. And the only thing we can put there and not change anything is going to be a 0. In other words, our asymptote in this case is going to be through y equals 0. Again, since that's just a single value, that's going to be a horizontal asymptote. And then the remaining rational function is actually just going to be the same as the original function. So 5x plus 6 over x squared minus 3x minus 4. All right. Now, obviously, if there's a quicker way to do this, that would be nice to know. And in fact, we can use those 3 examples to generalize to all rational functions in order to make it a little bit easier. So, if the degree of the numerator is greater than the degree of the denominator, and the example we saw of that was number 4, where the degree of our numerator was a degree of 2, degree of denominator was 1, then there's going to be a slant asymptote. And if that's the case, you have to divide. But for these next 2, you actually can skip the division if you'd like to. If the degree of the numerator is the same or equals the degree of your denominator, then there's going to be a horizontal asymptote this time through the value y equals a over b, where it tells us that a and b are the leading coefficients. In other words, on number 5, if we didn't want to have to worry about dividing, we could just look at our leading coefficients, 2 over 2, and say that our asymptote is through y equals 2 over 2, which is equal to 1, which in fact, if you notice, is the exact same thing we got right here. But notice that that's quite a bit less work than it was to have to do long division. Finally, if the degree of the numerator is less than the degree of your denominator, then there will still be a horizontal asymptote. This time it's going to go through y equals 0. And in fact, if you're wondering why that's always going to be the case, go back and take a look at number 6. If we were to get these to have the same degree, we'd have to put a 0x squared in front of 5x. At which point, notice that the degree or the leading coefficient for your numerator is 0, for your denominator is 1, and that's going to be y equals 0 over 1, which is just 0 for your horizontal asymptote, which again is the exact same thing we got right here. And that's always going to be the case if the degree of your numerator is less than the denominator, so you can kind of always use that as the asymptote. Okay, so let's put it all together. Let's take a look at number 7 and 8. We'll go ahead and graph a couple of these rational functions using all that stuff that we just got done discussing. Let's start with number 7. We've got f of x equals x squared minus 6x plus 8 over x squared minus 16. So first thing we're going to do is we're going to factor this. And in our numerator, our factors are going to be x minus 2 and x minus 4. As for our denominator, we're going to have a difference of squares. So our factors are going to be x plus 4 and x minus 4. All right, so first thing that we're going to find is any holes for our graph. In this case, notice that the factor of x minus 4 is going to cancel. That does give you a hole with an x value of positive 4. So then let's find the y value for that. When we cancel out those factors, our remaining function is x minus 2 over x plus 4. So if we want to know what the y value for our hole would be, we would take 4 and put that in for x. In other words, that would be 4 minus 2 over 4 plus 4, which becomes 2 over 8. And then that simplifies to be 1 over 4. In other words, we're going to have a hole on our graph at 4 and positive 1/4. So let's go ahead and draw that in. That's going to be about right here. All right. Next, let's go ahead and talk about our roots. Roots are anything left in our numerator. So if we have x minus 2 in our numerator, that tells us that we're going to have a root at positive 2, comma 0. Once again, we can go ahead and put that point on our graph. Now, we didn't really talk about y-intercepts, and that's because we really shouldn't have to. Remember, y-intercepts is really just where the function has a x value of 0. In other words, if we put 0 in for x, then our y value is going to be 0 minus 2 over 0 plus 4, which is negative 2 over 4, which when we simplify that is going to be negative 1/2. So once again, we have another point that we can graph at 0 and negative 1/2. All right, for vertical asymptotes, remember that's anything left in your denominator. So x plus 4 tells us that our asymptote, our vertical asymptote, is going to be through x equals negative 4. So again, remember your domain restrictions, which would have been that x cannot equal 4 or negative 4, become either a whole or x-intercept. Obviously, for negative 4, that was our vertical asymptote. For whole, that was the x equals 4. So let me go ahead and graph that asymptote in here. So negative 4, and here that is. All right, so one last thing to find, which is our horizontal asymptote. We are fortunate because our degrees at the beginning were equal to each other, so we can just look at the leading coefficients. And so our horizontal asymptote is going to be through y equals 1 over 1, or just y equals 1. And at that point, we have just about everything we need in order to create a graph. In fact, we've got everything we would need for the right half of our graph. Let me go ahead and draw that in here for us. Oops. So here is that right half. But notice that we don't have anything on the left half. We need some point to be able to put over here. So the easiest thing to do is to just pick an x value that's somewhere to the left of that vertical asymptote, which remember the vertical asymptote is running through at x equals negative 4. So really we just need to pick some point as an x value to the left of that. And the easiest is usually to just pick the one directly to the left. In other words, we're going to test another point. And this test point is going to help us with creating the left half of our graph. So our test point, we're going to use x equals negative 5, and we're just going to take negative 5 and put it in for x. Now, when you do that, you can either use this first option or this second option as far as your options for the function. And one of those is probably going to be quite a bit easier to use. I'm going to go ahead and use that second option, which is x minus 2 over x plus 4. So that's going to be negative 5 minus 2 over negative 5 plus 4, which is going to become negative 7 over negative 1, which simplifies to be positive 7. In other words, another point, which is on our function, is negative 5 comma 7. That just gives us one last point that we're able to graph, which is going to be right here. And then that tells us where we need to draw in the rest of our function, which is going to be in this top left portion of our graph. And there we have it. Everything that we saw in the previous video, we now have on this graph. Now, again, it took a little bit more work, but now we can hopefully see a little bit more about how the equation correlates to its graph. Let's do the same thing with number 8. So with number 8, let's go ahead and start by factoring as much as we possibly can. So for our numerator, we have a GCF of x. That'll leave us with x squared minus 4 inside the parentheses over x squared. And then that also ends up being a difference of squares. So we're going to get x plus 2 and x minus 2 over our denominator, which is just x squared. Okay, so the first thing is let's look to see if we have any wholes. We actually do have a factor which cancels out of both numerator and denominator. And so at least at first, it looks like we're going to have a whole through x equals 0. But the problem is, if we try to put 0 back into our equation to try to find the y value, we're going to end up with 0 plus 2 multiplied by 0 minus 2 over 0, which is a problem because we can't divide by 0. And in fact, it turns out that there is no whole. Although we were able to remove that discontinuity, there's something else happening there that's going to prevent us from having a hole. And in fact, we'll find out what that is in just a little bit. All right. Next is going to be our roots. Again, roots are anything left in your numerator. There's actually then going to be two roots. You're going to have -2, 0, and also +2, 0. As for your y-intercept, we'll go ahead and put 0 in for x to see what we get as our value. Notice that when we do that we put 0 in for x everywhere. That also means that we end up with 0 in our denominator. So for our y-intercept, there's actually going to be none for that as well. Now, vertical asymptotes are anything left in our denominator. Notice that we still have x in our denominator, which means that we're going to have to say that there's a vertical asymptote through x equals 0, which is why we didn't have a hole. Our vertical asymptote takes precedent over the hole that we would have had. In other words, you cannot have a hole on a vertical asymptote. So the fact that there's a vertical asymptote is the reason why we did not have a hole. So that's why we were running into some problems earlier trying to find that hole. Finally, for horizontal asymptote, it actually ends up being a slant asymptote, because if you notice, the degree of your numerator is greater than degree of your denominator, which means that this is the one time we actually need to do long division. So I'm going to go ahead and do that down here. We'll set up our numerator first. So x cubed plus 0x squared minus 4x plus 0, don't forget your placeholders, divided by x squared plus 0x plus 0. Again, make sure you've got your placeholders. Lots of them here. So we want for x squared to match up with x to the third. To do that, we're going to multiply by x. So that's going to give us x squared, or x to the third rather, 0x squared and 0x, which we are subtracting all of that. And that's going to become then, let's see, just -4x as our value that we are left with, which is in fact less than our degree of our divisor. So that becomes our remainder is a -4x over x squared. Remember that whatever piece of that is in front of your remainder is going to become your asymptote. In other words, we are going to have a slant asymptote through y equals x. So y equals x, you've got 0 for your y-intercept, and that becomes this line which runs diagonal through the origin. And that's actually all we need to be able to graph, because notice that we have a point on either side of our vertical asymptote. So we've got part of our graph that'll look like this, and the other part of our graph that'll look like this. All right, guys, so that is it. Hopefully that helps you with now seeing how the equation correlates to the graph. Until next time, have a good rest of your day.